Ooh, that's a crowd. Morning. We are going to take a look at a topic that has a degree of hype around it, but not on the same scale of AI, and probably doesn't quite deserve it yet, the future of quantum computing. And I think the good place to start, and it may well be that that's where we end, is, Seb, what is quantum computing?
Such an easy start. There we go. Yeah, so quantum computing is a new form of doing computations where basically these machines make use of very strange effects we find in the quantum world. Something being in two places at the same time, there's weird entanglement that gets thrown around a lot, and uses that to do computations in a completely new, better way, where the hope is that these machines will be able to solve certain problems that would take 1 million years to solve on a supercomputer in maybe minutes or seconds. So it's a completely different type of computer.
I mentioned the hype word. There is a lot of claims around quantum computing that we are going to be able to fill in the gaps when GPUs can no longer process the data required for the next generation of AI models. But your company, Universal Quantum, is taking a different approach. You're not going for the immediate hit. You're looking at the true utility of quantum.
Yeah, I think there's still a question out on, is there an initial hit, right? And I think you will hear a lot of talk around quantum in terms of what this technology may be able to do in the next couple of years. I think it's very uncertain if you follow the science. And I think what we do know today is that these quantum computers, we start talking around qubits, quantum bits, we really need to scale these machines from where we are at the moment, tens of qubits, hundreds of qubits, to millions of qubits. That's a scary target that we're aiming for here, but this is what ultimately must happen to unlock these applications associated with quantum computing, and this is what we really focus on. It's the hard route, but really long-term, it's the only route that one needs to take.
Hands up if you know what a qubit is, because if you don't, I'll ask him to explain it. All right, I think enough people know. It's basically a quantum bit. It's a way of measuring data in.
Yeah, so it's the very original wording, right? It's the quantum bit where this qubit can also be 1 or 0, like a classical bit, and that's how traditionally information is represented in our computers. But these quantum bits, in a very, very strange way, can be 1 and 0 at the same time. And this is where some of the computational power comes from. It's only half of the story, but in terms of how qubits go, that's really the power that they bring along.
Why do we need so many to do something useful?
Okay, so usually the theory would tell us that maybe a few hundred or a couple of thousands of qubits would be all we'll ever need. However, all quantum computers have errors, which basically means we're not that good at controlling these qubits, getting them to go from a 1 to a 0, these sort of things. So we introduce errors. These machines are very fragile. They're non-perfect systems. Yeah. The way to get rid of these errors, to actually get some useful computations out of them, is to what's referred to as error correction. It's a particular algorithm you need to run, very complicated, don't worry about it, but high level what this algorithm is saying is give me lots of qubits and I'll remove these errors for you. That is the reason why these large number targets are really out there. Now, you mentioned the short-term hits. There's a focus in the community on trying to get the most out of small-scale machines where you don't need to do this error correction, where you're trying to find applications that can live with these errors in some shape or form. And that is where, at the moment, we don't know if these applications really do exist. There's a lot of work going on there. But even if they do exist, the sort of large utility scale applications that we're really excited about, you've got to go error correction. You've got to hit that long-term goal.
There's multiple different flavors of quantum computing, to use a phrase. What approach is Universal Quantum taking?
Yeah, so lots of different ways, and this is where it gets complicated. Lots of different ways to build these very complicated machines. Number one, what we need a quantum system, something that exhibits these strange behaviors of being in two places at the same time or having a 1 and a 0 at the same time. And there's lots of different ways of doing that. You get some people working with what's called superconducting qubits. These are these chandelier pictures that you see when you search for quantum computing online. Some big players in that game using that technology. Trapped ions, so using charged atoms as our qubits is another promising one. That's a technology that we use. It is I think the world's best qubit currently available. And then there's a whole range of other ways to build these machines.
Let's talk about scale. You guys published a really fascinating paper earlier this year, big breakthrough technology in how to improve connectivity between and information sharing between different trapped ion systems without the use of a whiteboard and in language that I can understand. Can you explain that a little bit more and about how we scale quantum?
Sure. Whiteboards are great. I don't know what the worry is.
They didn't give us one, that's why.
Right. So the high level, the idea is that if you want to scale quantum computing, you need to have a modular architecture. And what I mean by that is that you get to a point where each module in itself, you can think of like a quantum computing chip, like a processing chip that we have at the moment, and you need to be able to link up individual chips or modules to make a bigger quantum computer. Now, it turns out making a quantum link between these quantum chips is outrageously difficult. It's what I think the whole sector views as one of its hardest challenges. And what we worked out, and we announced that at the beginning of the year, is a way of how that actually can work. We've demonstrated it with numbers that are already good enough for a 1 million qubit quantum computer. So for us, that's no longer.
So why don't we have a 1 million qubit quantum computer today then, if you've
We're
cracked
working
it?
on it. We're working on it. I think there's lots of challenges in quantum computing. It's ridiculously hard, I think would be fair to say. That one is one challenge. What we're really focusing on right now is to get each individual module itself to be fully integrated so that you can really look at this as a self-sufficient mini quantum computer. And the way we're designing and manufacturing these is that once we're at that point, give us a couple of years, then we can simply stitch these things together using this UQ Connect technology that we've launched very recently to really truly scale up. But it is hard. It may sound simple, but it really, really isn't, and this will take some time.
What sort of time frame are we talking? I mean, are we talking years, months, decades?
Yeah, I think it depends what you want. I think there is a hope that out of these sort of near-term machines, maybe over the next couple of few years, we can squeeze something out of them. These larger error-corrected machines, it would be nice to get some utility to something where you really feel a change because of quantum computing. Maybe a new drug was developed because of that. Maybe we understand climate change better. Maybe a new material, a high-temperature superconductor. There was some hype around that a few months ago. Maybe something like that will appear because of quantum computers. I mean, there's a huge push to do that this decade, but I think this can definitely leak into the next decade as well.
What are some of the, let's call them low-hanging fruits, what are some of the potentially early use cases for the first generation of, let's say, 10,000 logical qubits? A logical qubit is made up of error-corrected physical qubits. What's the first generation use cases?
Yeah, so these logical qubits are error-free qubits, the ones we really want to use. I think there's a lot of excitement, and me personally as well, around drug discovery. I think using these quantum computers to understand chemical reactions better, molecular structures better, which is at the heart of developing new drugs, and currently is really hard using our currently available computing technology. I think that's one that we're all very, very excited about. There's others as well, and you will find applications across all major sectors probably represented in this group. I'd be very surprised if you all won't in some shape or form be significantly impacted by quantum computer at some point in the future.
Let's talk about AI, because basically anyone that's walked around this incredible event for more than 5 minutes will realize AI is everywhere. Will quantum help bridge that gap in AI when we get to a point where GPUs aren't really cutting it anymore?
I think that's the belief. I think we probably have enough insight to be able to say that quantum computing will have a significant impact on AI. It will accelerate AI quite dramatically. Some people would say it's the only way to make AI really go all the way. I think that we do know. Again, it will take a little bit of time to get these machines to be large enough to be able to do exactly that. But I think, that's definitely one application. And at the same time, and I find, really exciting as well, is that we can leverage AI, right? The way we build machines, we make use of AI, and we're going to significantly accelerate and support AI. It's a really nice symbiosis, I think, that is there.
the rise of generative AI, the rise of large language models, of foundation models, had an impact on the way that you're investigating the development of your quantum chips?
Yeah, we do use some form of that. I can't say too much about that, but it has an impact, right? And our software engineering teams, they obviously love some of the features that are coming out there. I wouldn't say it's revolutionizing our way of doing quantum computing at the moment, but it's a part of the secret sauce, so to speak.
Now, generative AI has been around for a long time. It's not a new thing. It didn't arrive with ChatGPT, but ChatGPT seemed to have created that human moment, the point where everyone woke up and said, well, actually, maybe we could be using this. When is that moment going to come for quantum, and do you have any indication of what that might be?
Yeah, so I think there's two moments, if I can choose two. One on a technical aspect, and one on more the sort of human level, and I'll start with the latter first. It's around this generating utility from quantum computing. So these machines doing something you couldn't dream of doing today. I think that, like I said, is something we would love to do this decade. I think the other one is that when you, and I don't want to go into too much technical detail, but if you follow quantum computing a little bit, then people keep talking about, like, oh, we've got more qubits and we're scaling. But actually, if you look at it, it's ridiculously slow. If you understand where we need to go to, it is depressingly slow. So we have to change the scaling of these qubit numbers, in my opinion, to really move this forward. And I think when we can get to the point where we can show that inflection point where the number of qubits, high quality qubits we have available, exponentially increases, that in itself should give people a lot of confidence that this is not around the corner, but pretty much around the corner.
So around the corner in deep tech terms could be about 10 years. It could be.
But here's, no, shorter than that. I
think
if we get into that, and this is why we at Universal Quantum, and I don't want to focus on our technology necessarily, but the sort of relentless focus at the moment is to unlock that exponential scaling, that whatever we build today, we just need more of the same to scale up and not have to reinvent the wheel, not have to come up with completely new solutions just because I'm trying to make these machines just a bit bigger. And this is what generally happens at the moment in quantum computing.
And quantum is a very radically different approach to computing. It works in a different way. But you are trying to utilize existing infrastructure, existing technologies, fab construction, rather than reinvent the wheel. Is that right?
Yeah, absolutely. I think, so lots of ways of building these machines. You will find that some of them, which on paper look really, really good, you do have to invent new fabrication processes and so on. I think that presents some challenges. We focus on really leveraging what's already out there. I don't want to have to redevelop a multi-billion-pound silicon fab process, right? I think that would be madness. So we're really trying hard to use what's already out there and just put this together in a unique way so that these machines work the way they should.
Let's say we get to this magical future, 10, 20 years' time, where we've got multi-million qubit systems that are doing amazing drug discoveries. How do we verify that the information these quantum computers are producing is real, and we don't end up with some situation like we're getting with hallucinations from AI? Can we ever verify it? Can we check? Will we be able to create classical systems that can verify it?
So I think there's a whole mini sector around how do you verify something. You can't just simulate on a classical computer. There's no easy check you can do on some of the outputs. There are obviously certain things like these machines will be able to break large encryption codes. So the way you secure your data at the moment will no longer be secure, most likely, if quantum computers are around. Very hard to break these codes, but you can check it very, very quickly. I think another approach also is to obviously have lots of these machines and just check that different approaches give you the same answer. You don't want to have to step on an airplane and hope that quantum computer, that one machine, really did the simulation right.
So much like we use classical computers to check each other's work now, we'd use different types of quantum computers.
Right.
Do you think one flavor, and I'm going to keep using the word flavor, sorry, I know it makes it sound quantum computing sounds like an ice cream, but do you think one type of quantum computing will win out over the others? And I'm assuming in your case you think it's going to be trapped ion, but do you think that we'll see an environment where there's different types of quantum computing for different use cases, or will one architecture win through?
I mean, it's not just trapped ion, it's universal quantum, right?
Yeah.
No, but on a serious note, I think these hardwares, they come with their pros and cons. Yeah. And my view would be that provided they can get to that larger scale, it will crystallize that some of them will be better suited for certain applications than some other ones, and it will then start to divide the space up a little bit. I think we can already see that in the clock cycles, just how these machines naturally work. But I think the first question is, can they actually get there? And often, if I can just spend a minute on that, is you know, people will evaluate a particular hardware approach and will say, oh, those ones run a bit faster, or they have a slightly better fidelity, therefore they're the best one. But if they can never get 2 millions of qubits, the whole argument is mute. So you've got to look at the whole thing together. You
mentioned security earlier on. Post-quantum cryptography is becoming a big thing. Every company should be looking at it now, if they're not. How long do we have to prepare? When is a quantum computer going to be able to run Shor's algorithm? And if you don't know, Shor's algorithm is the algorithm that would crack RSA encryption and existing encryption tools. How long do we have to get there?
Yeah, so I think number one, and I know there's a lot of businesses in the room, please, please, please look at your encryption algorithms and check if they are quantum secure. There is a lot of work being done also by NIST in the US to come up with a set of encryption algorithms which, to the best of our knowledge today, protect you against a quantum computer attack. Please make those changes. Now, you may now think, well, you just told us it's going to be maybe 8, 9, 10, 11 years away. I have time. What we're already seeing at the moment is that certain entities, people are stealing data that has a shelf life of more than 10 years, and they would just wait until a quantum computer comes along to break that particular code. So it is absolutely imperative to think about that today in preparation for these machines coming, because I guarantee you, quantum computers will be there at some point in the future. So you have to think that way.
How do we secure quantum computers? Is it a technology that, let's say we get to that future point, should be controlled by large-scale government entities, or do you see it as something that will be as ubiquitous and widespread as any high-power computing system today?
Yeah, it's a great question. It's a huge worry, right? And I'm going to talk personally right now.
Yeah,
don't associate that to Universal Quantum or investors or anything. But there's obviously a worry that there will be a time, like ChatGPT moment, all of a sudden there's utility and people will want to use these machines. I have a fear that all of a sudden it will be the multinational companies who will just come in, buy up all of the time of these machines and make their drugs a bit more expensive, not claiming that they are doing that, but they may be able to do that. What happens to a small startup, a very smart person somewhere where they don't have the means to buy themselves into this sort of architecture? I think there, and you know, we're in the process of setting up a foundation that will make sure that this resource is allocated as fairly as possible, up to an extent. We have to make money.
Still got to make money,
make money. But I think that's one point. The other side on the security part is that these are national assets in many ways, right? There's a sovereign capability I think every major country needs to have, given its impact, its implications on security and its economy, and therefore you have to think about how to protect those assets. And I know many governments around are putting things in place to protect us, the startup community, these machines that are being built, but there's a lot more work to be done around that.
I imagine the quantum computing sector has the same problem as any tech sector around skills and recruitment. If someone's looking, I don't know if there's any students here today or looking early in their career, if someone was looking at potentially getting into quantum computing as the big technology of the future, what should they be researching? What should they be studying? Where are the entry points?
Nothing special. You do not need a quantum background to work in this field or at companies like Universal Quantum. In fact, most people who work for us do not have a quantum background. The reason being that we want the best engineers to build a particular part. I don't want a quantum physicist to build a quantum computer. I don't think that's how it's going to work out. They are still very important. Let me be very clear on that. But we need all different skills. It's a very interdisciplinary team that we have and that other companies in this space have, because you want to make use of all the different technologies out there to actually build these machines. So it's not, you don't need a quantum background, you do not need a quantum physicist. Just be excited about what we're trying to do, and you will find your way in.
What about software? Because I imagine we've got a lot of developers here today. how hard is it to build software for quantum computers, and how different is it to building for classical computers?
Yeah,
And high-performance computers, I think, is a good comparison.
Some of it is very, very different, and the way you program a quantum computer is very different, but a lot of it is also the same. The higher up you go in the stack, the more it will look like what we currently have in our computing infrastructure and the way you access these sort of machines. So just to be clear, the usual thought way is that these machines are accessed via the clouds. In fact, you can already access quantum computers via the clouds, and people are working very hard to abstract the quantumness away from it, so that you do not need to be a quantum expert to use these machines.
Yeah.
You need to understand how these algorithms maybe work and give you a benefit, but generally you can program in Python and there's a quantum black box that you can drop in. You don't need to worry about the rest. However, some of the software experts that we have as well, when you work on the lower stack, you do need to start to think carefully about how these quantum systems, these qubits, how they react, what they like, what they don't like, and that really changes the way you program. And then on the very, very top, just to develop these algorithms, these quantum algorithms, is a completely different ballgame to conventional algorithms.
Right.
That's the other thing to note, and that's seen as really hard to develop these quantum algorithms. That's a science of its own.
And they make better use of spatial awareness rather than just a logical point-to-point, don't they?
Yes. Yeah.
Yeah, okay. So, all right, we've got a couple of minutes left. Couple of last questions. What is, aside from the prospect of navigating the hype, what is the hardest thing about building a quantum computing company today?
There's so much.
2 minutes.
2 minutes, there we go. I mean, I think, so one, and again, it is not easy to build these machines. Please don't go away from here and be like, oh, they figured it all out. You push absolutely everything. Everything we touch, we push to the absolute limit, but we don't need to go over, which is the great thing. That's hard, but a lot of fun. Yeah. I think money is always an aspect, and money does talk in this game. And I think, we're seeing a lot of capital flowing in. I think a lot more obviously has to happen, and of course I would say that, but it really is the truth. And I think we're looking to governments as well as the usual investment community to keep supporting this growing ecosystem. And I think it's also around talent. We have to get the world's best people in. There aren't that many people who can do some of these things. So that's another area.
So let's go to the positive side. Working in the future when we've got 1 million plus logical qubits, we've got a point where, sure, as algorithm's been cracked, but everyone else has managed to do the right thing and move to post-quantum algorithms. What is the one thing about quantum computing at that scale that excites you the most?
For me, it's the drug discovery side.
Okay.
The reason I got involved in this space is, and this sounds cheesy in a way, but really wanting to do something very, very positive for people. There are some dangers to this technology, like with any technology, but the upside, I'm utterly convinced that this technology will be such a game changer for humanity. Drug discovery is just one of the examples that I think will be huge. I think that really, really excites me a lot on a day-to-day basis.
And will quantum computing replace classical computing, or will there always be room for classical computers?
No, definitely not. There are lots of things quantum computers are terrible at. You would never want to go to a quantum computer with those sort of problems. And really what one envisions is a hybrid computing architecture where actually you just care about your problem being solved, really, right? You submit that problem, and there's very smart compilers that decide, hey, this bit goes to a quantum computer, that bit goes to a conventional computer, do your thing, we'll stitch it together, and you get an answer out.
Fantastic, thank you. Well, I suppose the sum up is that it's coming, it's not here yet, but if you run a company, make sure you're not using RSA encryption and that you're fully upgrading to the NIST compliant algorithms in the future. That's great. Thank you.
Thank you.